This is part 2 of our discussion of acid-base chemistry. So here I want to start out by talking about the Bronsted-Lowry definitions of an acid. So by these definitions, an acid is any species that donates hydrogen ion, which is not really that different than the Arrhenius definition. But the difference is here, and that a base is defined as any species that accepts a hydrogen ion. So, for example, if you look at ammonia, now ammonia is soluble in water, it's a weak base, solutions of ammonia are basic. Where's the hydroxide coming from? It's not a base by the Arrhenius definitions, but it is a base by the Bronsted-Lowry definitions. So like I said, where's the hydroxide coming from? Okay, the solution is basic because the ammonia reacts with water to form ammonium ion. In other words, ammonia is stealing a hydrogen ion away from water, and what's left over then is hydroxide. Or you could think about it this way. If you look at the autoionization of water, okay, if you look at the autoionization of water, this is an equilibrium reaction. And we already talked about in the previous video how in a neutral solution these two are equal to each other, being 1 times 10 to the minus 7th. Now, if you remember Le Chatelier's principle, when you upset a system at equilibrium, it seeks to readjust or reform the equilibrium. So if we start out in the neutral water, these two are equal to one another. Okay? Then we start adding ammonia. So ammonia reacts, you could think of the ammonia as reacting with the hydronium component. So basically the ammonia is removing hydronium ion, right? So this is basically being taken out of solution. And so what happens according to Le Chatelier's principle is the reaction is going to shift to the right to replace what we took out. Okay, and so in the process of doing it, when we started out with the neutral solution, these two were the same. Now we add ammonia. The ammonia starts removing hydronium. The reaction shifts to the right to take out the hydronium, but shifting to the right produces hydronium and hydroxide. So now the concentration of hydroxide is going to be greater than that of the hydronium. Okay. Now, what we call the conjugate base is the substance that is formed when an acid loses its hydrogen ion, right? So, for example, then, acetate is the conjugate base of acetic acid. Okay. Similarly, the conjugate acid is the substance that's formed when a base gains a proton. Okay, so then, for example, acetic acid is the conjugate acid of acetate. Okay, so what's a base, or what's an acid rather? An acid is a proton donor. So once the acid gives up that proton, what's formed is the conjugate base. So a base is a substance that accepts a hydrogen ion. So when the base accepts the hydrogen ion, it becomes the conjugate acid. So acetate is the conjugate base. Acetate is the conjugate base of acetic acid, and acetic acid is the conjugate acid of acetate. So here we have another important relationship that you need to know. For any conjugate acid-base pair, the product of the acid dissociation constant and the base dissociation constant is equal to Kw. Okay, so for example, if we write this out, okay, acetic acid plus water makes acetate plus hydronium. How do we write the Ka for this? Concentration of acetate times concentration of hydronium divided by concentration of the acid. That's the Ka. Okay. Now, the acetate is a base. So what happens if we have some source of acetate, neutral source of acetate ion like sodium acetate, it seeks to reestablish the equilibrium with acetic acid, right? Because you know this reaction here, the dissociation of acetic acid favors acetic acid. You have probably 90 something plus percent over here in the form of acetic acid. So what happens is, think about Chatelier's principle. If we add acetate, it's going to shift it this way, right? So if we have no acetic acid, if we're starting with just pure acetate, it reacts with water, forms acetic acid anyway. We write Kb is concentration of acetic acid times concentration of hydroxide divided by concentration of acetate. Now, so the product then, you can write this out if necessary. You can write this out to prove yourself that this is true. In fact, let's do this. So Ka, what's Ka? So Ka is concentration of acetate okay, times concentration of hydronium divided by concentration of acetic acid okay, and Kb is product, or rather is concentration of acetic acid times concentration of hydroxide divided by concentration of acetate. Okay, and if we write all this out, and we cancel, acetate cancels, and acetic acid cancels, and we're left with concentration of hydronium times concentration of hydroxide, right? So Ka times Kb is equal to Kw, okay, for any conjugate acid-base pair. Now, anytime the product of two numbers is a constant, that means that as one number goes up, the other number must go down. So as Ka gets bigger, Kb gets smaller, and vice versa. So the weaker the acid, the stronger the conjugate base, and the stronger the acid, the weaker the conjugate base. Okay, so let's look at an actual example here. Okay, so let's suppose we have acetic acid versus hypochlorous acid. Okay, so the Ka for acetic acid is 1.8 to the minus fifth, and the Ka for hypochlorous acid is 3.0 times 10 to the minus 8. So right off the bat, before we go any further, let me ask you this question. Which one of these is the stronger acid? Okay. Which one is the stronger acid? How do you tell that? Which one has the biggest equilibrium constant? Okay. So here this is 1.8 to the minus fifth versus 3 times 10 to the minus 8, which is the bigger number. This is by roughly 3 orders of magnitude, right? So that's the stronger acid. Okay, so of the two, that's the stronger acid. Now let's look at the two conjugate bases. Okay, so we're going to use the relationship Ka times Kb is Kw, rearrange it to solve it for Kb. Kb is Kw over Ka. So the Kb for acetate is 1 times 10 to the minus 14th divided by 1.8 to the minus 5th. That's 5.6 times 10 to the minus 10th. Okay. And for hypochlorite, that's 1 times 10 to the minus 14th divided by 3 times 10 to the minus 8th is 3.3 to the minus 7. Right? So let me ask you now this question. Out of these two numbers, which is the bigger number, right? And this is by roughly 3 orders of magnitude. So this is the stronger base. Okay, so again, so as the acid gets stronger, the base gets weaker. So stronger acid, weaker base, and weaker acid, stronger base. So this just repeats what we set up here. Acetic acid is a stronger acid because 1.8 times 10 to the minus 5th is bigger than 3 times 10 to the minus 8th. And hypochlorite is the stronger base because 3.3 to the minus 7th is bigger than 5.6 to the times 10 to the minus 10. Alright, so let's talk about, calculation of pH of a weak acid. Now first of all, before we get too far into this, I want to say you should be able to see how the pH of a strong acid should be a simple calculation. Okay, why is that? Because a strong acid is 100% dissociated. You simply take the negative log of the concentration and that's it. So let's say if we had 10th molar hydrochloric, you'd take the negative log of 0.1, which would be -1, and your pH would be 1. Okay, but not so with a weak acid, because we have to solve an equilibrium. Okay? To get the pH of a weak acid, we have to do an equilibrium calculation. So, start out by writing our reaction. Alright, so the acetic acid dissociates in water to produce acetate ion plus hydronium ion. So we're starting out with no acetic acid, or no acetate rather. And so of course it's going to shift to the right. These are going to go down. Acetate and hydronium, will go up, and this will go down. So we'll let X represent the extent of the dissociation. In other words, how far does this reaction go to the right? So these will go up by X, right? And this will go down by X. Okay, and basically we're going to set that equal to the K, to the Ka, and solve it for X. Okay, so acetate one more time. Acetate will equal hydronium, and that will be X. And what we're going to do is the concentration of the acetate would be 0.1 minus X, but what we're going to do is assume that that's approximately equal to 0.1. In other words, we can neglect the effect of the dissociation. If you remember when we talked about equilibrium calculations, this was one of the cases that we talked about, where if you have a small k, you can basically neglect the effect of the dissociation. So instead of x squared over 0.1 minus x, it's basically simply x squared over 0.1, right? And so now we can cross multiply. So you take 1.8 to the minus 5th, we'll take 1.8 to the minus 5th, cross multiply, so times, multiply it by the concentration, which is 0.1, take the square root, and what do you get? 0.001 134. Okay, or 1.34 times 10 to the minus third. You take the pH of that, and you get 2.87. Okay. Now just remember, if this had been a strong acid, if this had been 0.1 molar HCl, our answer would have been 1. So we're, changing almost 2 pH units. Okay. So now let's do the same calculation except for a weak base. And we're going to be doing almost the same thing, except that there's one extra step that we have to do here. Alright, so what is the pH of 10th molar ammonia? So Kb is, if you look up the dissociation constant for ammonia, Kb is 1.8 to the minus 7. And by the way, it's a total coincidence that happens to be the same Ka as for acetic acid. A total coincidence, you're talking about two different chemicals, two very different chemicals with two different reactions taking place. One's an acid, one is a base. So coincidence, that's the same number. So anyway, let's start out with our reaction. Okay, so one more time, why is ammonia a base? Because it abstracts, it removes hydrogen ion from solution. Okay, so basically it's stealing hydrogen away from water and forming ammonium. So one more time, we'll let X represent the extent of the dissociation. The reaction is going to shift to the right. These will go up by X. Okay, and these will go down, or I'm sorry, not the water, but the ammonium. The ammonium will go down by X. Okay, and so X will be concentration of ammonium will equal concentration of hydroxide, that will be X, and concentration of ammonia will be 0.1 minus X, which we're going to assume, again, we're going to neglect the effect of the dissociation on the concentration of ammonia and assume that 0.1 minus X is equal to 0.1. So now the equation that we have to solve comes down to X squared over 0.1 is equal to 1.8 to the minus 5th. Solve it, X, you get 1.34 times 10 to the minus 3rd. And you take, which is basically so far, because the Ka's or the K's are the same, this is exactly the same numbers as in the last example. So we come down here and you take the negative log of that and you get 2.87, except that's not the answer. And you say, why not? Because in this case, we're now doing a base problem, and X represents hydroxide. Okay, and you were asked to solve for the pH of the solution. What is the pH of the solution? So 2.87 is now not the POH, it's not the pH, it's the POH. So to get the actual pH, we have to subtract that from 14, and that comes out to be 11.13. Okay. Now, there's two more calculations we need to do. There's actually 4 total. Salt of weak acid, the weak base, and then salt of a weak acid and salt of a weak base. Okay, so we've got 2 more calculations to go. So, suppose they ask you what is the pH of 10th molar sodium acetate. Now, first of all, the sodium ion is simply a counter ion for the acetate. Acetate is an ion. It can't occur by itself in a compound. There would have to be something else there to balance the negative charge. So this thing dissociates. When sodium acetate dissociates, it gives you sodium ion plus acetate. Okay, so Sodium ion really doesn't do much of anything. Like I say, it's just a counter ion. It's just a counter ion for the acetate. The acetate is where the acid-base chemistry takes place. All right, so acetate is the conjugate base, of acetic acid. So in acetate, what happens to acetate in water? It starts to reestablish this equilibrium to form acetic acid. In other words, it starts taking hydrogen ions away from water to form acetic acid. Okay, so we know we're set this up the same way we did before. We know the reaction is going to shift to the right. Okay, so these will go up by X. We're going to form X moles of acetic acid, and we're going to form X moles of hydroxide, and our concentration of the acetate will go down by X, okay, so that the equation that ultimately we're going to solve will be X squared over the concentration, which was 0.1, is equal to the equilibrium constant. But what equilibrium constant do we use? We can't use 1.8 to the minus fifth. That's the Ka for acetic acid. We want the Kb for acetate. So one more time, we're going to use the relationship Ka times Kb is Kw, or rearrange it and say Kb is Kw over Ka. 1.0 times 10 to the minus 14th divided by 1.8 to the minus fifth is 5.56 times 10 to the minus 10. That's our Kb. Okay. So now, our equation that we have to solve is X squared over 0.1 is 5.56 times 10 to the minus 10. Like before, we're going to neglect the effect of the dissociation and assume that 0.1 minus X is equal to 0.1. I didn't spell it out here, but that's what I did. All right, so we're going to cross multiply. So we're going to take, so to get, we backtrack just a second here, and so to get the Kb, we take 1 to the minus 14th, that's Kw, divided by Ka, 1.8 to the minus fifth. That gives us Kb, which I rounded up to 5.56. Then we're going to cross multiply, so you multiply that by 0.1. Okay, take the square root, and you get what? 7.46. I rounded it up. 7.46 times 10 to the minus sixth. Take the negative log of that, you get 5.112. But again, this is not the answer, because again we're doing a base problem. X represents hydroxide. So when we take the negative log of this number, you get 5.12. Okay, subtract that. So when you take the negative log of that, that's the POH. So to get the actual pH, you have to subtract that from 14. 14 minus 5.12 is 8.88. Okay? Now we have one more case to go, and that is, I'm going to skip that page, salt of a weak base. This is our last case. All right? So as an example, let's calculate the pH of 10th molar ammonium chloride. All right? So just like in the last example, we're basically going to have an ion that's just a counter ion. Okay, so the real acid, the acid-base chemistry here is taking place with the ammonium ion. The chloride is just a counter ion for ammonium. So first of all, the ammonium chloride, it's a soluble salt. When you dissolve it up, it's going to dissociate into ammonium ion and chloride. So chloride is just a counterion for ammonium. Chloride has no acid-base properties. Okay, the ammonium is where the action is taking place here. So the ammonium dissolves up in water. Now remember, ammonium is the conjugate acid of ammonia. So it's going to seek to reestablish that equilibrium with ammonia. In other words, it's going to want to give up a hydrogen ion and become ammonia. So ammonium ion plus water becomes ammonia plus hydronium, right? We're transferring a proton. The hydrogen ion is basically giving up a proton, which is attaching to the water. Okay, so NH4 plus to NH3 loses a proton, and that attaches to water and becomes hydronium. Okay, so we'll set this up like we did before. Okay, it's going to shift to the right. We don't know how much, so we'll let X represent that and then set it equal to the equilibrium constant. So these will go up by X, and the concentration of ammonium will go down by X. Okay, and we're going to make the simplifying assumption that 0.1 minus X is equal to 0.1. In other words, neglect the effect of the dissociation. So the equation that we have to solve will come down to X squared over the concentration, which is 0.1, is equal to K. So the only other thing we have to worry about is what do we use for a K? We can't use 1.8 to the minus fifth. That's the Kb for ammonia. We want the Ka for ammonium ion. So one more time, we'll use the relationship Ka times Kb is Kw. Rearrange it to solve it for the Ka. So Ka is Kw over Kb. So 1 times 10 to the minus 14th divided by 1.8 to the minus fifth, you get the same thing as in the previous example, 5.56 times 10 to the minus 10th. So what we have to solve comes down to X squared over 0.1 is equal to 5.56 times 10 to the minus 10th. So cross multiply, take the square root, right? Same thing we got before, 7.46 times 10 to the minus 6. Take negative log, you get 5.112. And that's the answer. Okay. Now we don't subtract it from 14. Why? Because here X represents hydronium. Okay, so when we take the negative log of that, what we're solving for is the pH, which is what the problem is asking for. Okay, so that's 4 cases: the weak acid, weak base, and the salt of a weak acid, and the salt of a weak base. Now, you might have noticed every single problem was really set up the same way. It comes down to X squared over the concentration is equal to the equilibrium constant, and cross multiply and take the square root. The only 2 things that you have to be careful about, you're setting every one of these up the same way. There's 2 differences. You have to watch out what you're using for a K. You have to be sure you're using the correct equilibrium constant. And then second of all, you have to pay attention to whether you're doing an acid problem or a base problem. If you're doing a base problem, then you're solving for hydroxide, and when it comes down to taking the negative log, you're getting the POH, not the pH, so you have to take that extra step of subtracting it from 14 to get the pH. And we're going to wrap up the second video.